Hello, this is again the Renewable Energy Technology course. I am Miro and we're back to the lecture on wind turbines and wind power. Still lecture number 2 on mechanical components and maintenance issues, but now we will have a very quick overview of some, let's call them operational issues related to components. Now these issues actually belong to all different parts of the lecture, but I have summarized some important issues here that need to be mentioned. On the other hand, we can talk about those much longer. But let's keep it short. Do not forget that the wind speed is varying all the time, always and everywhere. So a turbine, regardless of how it is made, how big it is and how complicated it is, it will actually operate at partial load most of the time. And how partial the load is depends, of course, on what kind of size of the rated capacity you choose. Having a big generator, definitely with a small wind rotor, would mean that you would hardly reach the rated capacity. You would need very strong winds to be able to load the generator properly. At the same time, if you actually are running a big generator with only a small power output, this is very bad because, well, it can work, but the electrical generators and electrical machines in general, they are not very efficient at deep part load. Regardless of how well they are made, of course, you can improve them and make them better, but generally, electrical machines lose efficiency a lot at part loads below 50%. Any other machines actually do that. So if you're running a 3 megawatt, say, electrical generator at 100 kilowatt output, you would not get anything out. This would all go into losses. So if you would be using mostly low wind speeds, you better optimize your machine for those low wind speeds. How to choose the generator size is a very important primary design aspect. And you should start, if you are designing a machine from scratch, you should start actually with a decision how to match the generator and the rotor. Quick example, even if there's probably a better example out there, but I deliberately take it from an old book just to show, well, about an old style stall-controlled, small comparatively, fourth generation wind turbine, just to show really the problem here. You can select 2 different generators. So say the rotor is fixed, doesn't matter how big it is. The rotor is fixed, and if it were operating at variable speed, it would perform approximately like this. So it delivers some power to the generator. At strong winds, definitely you would need to dump most of that power. And if the strong winds are prevailing, of course you would put a generator that is able to produce a lot. There's a lot of energy in the wind at high winds. So choosing a big generator, it would definitely deliver much higher power output in the strong wind or high wind spectrum. However, this machine, if it is a single big generator, actually would perform very poorly at the low wind speeds. And in the range of 5 to 8, 9 meters per second, those are the prevailing really anywhere wind speeds. Those are the winds that occur most of the time. And big generator would not deliver much there. You would see here, now using this as a rough example, actually the generator would not deliver any useful power output below 6 meters per second. To handle this problem, you would probably select a smaller generator. This would mean that now having the same wind rotor, you are able to produce actually power at low wind speeds. You're still producing fine, far below 6 meters per second. Actually, you're using the available power from the wind rotor very nicely. The generator here, the small one, has the chance to be very efficient. It is not in such a deep part load. But at high winds, definitely this generator would be soon overloaded, and you cannot really take care or use, put into purpose the big amount of energy in the high winds. So what to do? Definitely there is a trade-off. And one choice is actually to use two generators. The old wind turbines, the stall-controlled ones with induction machines, actually they did use, most of them, two different generators. They can be of different size, of course, and also of different pole pairs. The first generator would be the small one. This is the same example for the same turbine as the slide above. The small one has a larger amount of pole pairs. It is able to rotate at lower RPM and allows the wind rotor actually also to rotate at lower RPM, which is better for the low wind speeds. So at wind speeds 6 meters per second and below, the rotor with the small generator are perfect, very well matched. Towards the slightly higher wind speeds, from 8 meters per second and above, the rotor would be driving another bigger generator. Its performance, of course, and RPM is made to match or to use properly the available power from the rotor and convert it to electrical power without deeper partial loads in the high wind spectrum, the bigger generator here. This definitely allows for even if two-step, not really so fully variable, but it is a certain variability for the aerodynamic performance, for the wind rotor. These are just some examples how real, actual wind turbines looked like in the old days. You can use two generators of the same size and actually run only one of them at low winds and then run both of them at high winds. Or you can use generators of different sizes, as we talked about above. One big one for the high winds, one small one for the low winds. Later on, especially in machines which are still out of operation of the megawatt size, those solutions now through this special design, tailor-made generators, were able to be handled or inbuilt into the same generator. So generators for wind turbines, they were produced with the ability to switch pole pairs inside, and thus now acting as a small generator and then a big generator with the same machine. Another example of how now to match the rotor to the generator size related to what wind resource we have to handle. This is a real-world example from a machine, again a bit old, but actually many of those are operating out there. It's not a small one. It's a 80-meter rotor diameter with a 2.5 megawatt generator in the first example, then the same machine with a 90-meter rotor diameter, but with a smaller 2.3 megawatt generator. And you can compare the performance. Definitely this one here is targeting a market with generally low wind speeds. In the typical example, this machine was made for the southern parts of Germany. The wind resource is not so big there, while this one was made for the northern parts of Germany, the North Sea coast, where the wind resources are much more serious and possible to harvest. So the small rotor with the big generator, of course, would reach full capacity first at 15 meters per second. The bigger rotor with the small generator is able to reach full capacity already at 13 meters per second. You may think this is not a big difference, but actually the overall annual energy output from these machines, if compared at, say, the same wind speeds, this one would produce much more. It's actually able for a longer amount of time to fully load its generator, thanks to the larger rotor. Of course, at very high winds, if those would be prevailing, you would choose the bigger generator, definitely, because at high winds, you're able to produce 200 kilowatt active power output more. This is one example from the modern wind market. Actually, even now, manufacturers and anytime really, and all of the wind turbine manufacturers, they are offering all of their models and makes into different modifications targeting high wind or low wind market. And the latest Siemens machine actually is using a rotor, even if now this particular example has a special designed blades. It's actually using the basic concept for the blade that was the 60-meter blade that was made for the 5 to 6 megawatt turbines. But improving it even further, shortening it a little bit, still having 120 meters rotor diameter, and using only a 2.3 megawatt generator is definitely fitting the turbine much better into the low wind speed spectrum. How the wind actually blows and how the wind speeds are distributed around the year in terms of how often a certain wind speed occurs is, of course, very important for the overall capacity factor, or the overall productivity of the machine. And this is just one example, again, from the real world. It is an actual measurement for the wind speeds in the offshore wind park Horns Rev on the western side of Denmark in the North Sea. And you can see, really, this is a nice windy location, very good wind resource. Still, if we say that the average wind speed is 9 meters per second, the typical distribution, the so-called Rayleigh curve, would actually show that you still have the winds from 4 to 9, which are actually carrying the most amount of energy because they occur most of the time. Then 10 to 12 meters per second, you have really much more energy contained in the winds. And those winds also occur quite often. So you better use them properly. But then again, even if a very, very windy place would feature the high wind speeds not occurring so often. So definitely you have to optimize your machine for the low winds. Still being able to reach full capacity not below 13 or minimum 12 meters per second, because then you wouldn't be using the high wind spectrum and you would be actually losing a lot of energy. This is what turbine manufacturers are usually presenting in their brochures. Just a very quick review here. We don't need to stop much into this. The power output annually from a typical wind turbine, or from a given, let's say, wind turbine, can be calculated in this way. How long time, percentage of hours within a certain spectrum of time, say 1 year, a wind speed occurs, how exactly productive your turbine is at that wind speed, typically if everything else is all right, standard conditions, and summing them up for this particular standardized wind speed distribution, you can actually summarize this for the average wind speed of, say, 6 meters per second. Average wind speed still means that you have a distribution of different wind speeds in approximately this way. A machine, for example, this one here, of 2 megawatt, can be producing approximately 4 gigawatt hours per year. All other parameters standard. This is what the turbine manufacturer would show you. And this is, say, the guaranteed output for this standardized wind speed distribution, for this average wind speed, everything else normalized, and so on. Of course, this performance would change a lot. First of all, if the machine is not as reliable as it's supposed to be, if something goes wrong. Second, if the wind speed distribution is not exactly the standard one, definitely, and it often is not the standard one. And third, if you put your machine at a location where the air density is not the standard one, the turbulence is not the standard one, if you have very turbulent air field, your machine, first of all, will not be as productive as it is supposed to be, and second, it may suffer from damages, failures, and so on. Quick summary, the capacity factor of the wind turbine is actually influenced a lot by the chosen match between generator and rotor. Larger rotors are much better fit for low wind locations. And if you know that you are installing your machine in prevailing low winds, you better choose a larger rotor and a small generator. It will be more productive than the same machine with a bigger generator. Improving the part load efficiency is very important, both for the wind rotor aerodynamically and for the electrical machine, the electrical generator. There is no machine that is able to work efficiently at deep partial loading. And improving the electrical aspects, both generator and related power electronics regarding deep partial loads, is very important. You can actually harvest a lot more power if your generator is efficient at part loads. Thank you. And the next section will be the last one for the lecture on mechanical performance.